here's the final of the three ways which heat's going to be transferred. So we've dealt with conduction, which required a solid and you had fixed particles and the energy was passed from one particle to another. We talked about convection, where you had to have molecules that could move and the heat was transferred as the molecules actually moved and took that heat with them. The third one is radiation. And the reality is that any object, any body, which is above absolute zero, radiates heat. So it doesn't matter what it is. So you've got any object, and it's got some heat compared to what's going on around it. So this is my object. The sun is a classic example. And that just gives out radiative heat. Okay, and it doesn't require any particles to take it away. It's just given out. I mean, you can tell, you stand out and hold your hands up to the sun, and you can feel the warmth of the sun. And there's quite a lot of space between the sun and you, where there's not a lot of air or anything else to carry that heat. So the heat energy is getting away from the sun, it's getting across millions of kilometres of space, it's arriving at the Earth's atmosphere, then it's coming through the air in the Earth, and it's able to warm up your hands. So somehow the body, which is the sun, is losing this energy into a space where there's no fixed particles for conduction and there's no mobile particles for convection. It's happening through a vacuum, and this is what we call radiation. So radiation does not require a medium for the energy to be transferred through. It's transferred by way of photons, which are emitted from the hotter thing. And we're going to just have a formula again for measuring this, and we're going to look at how heat is transferred from a hot body into a colder surrounds, because very seldom is it actually transferred into something which is at absolute zero, but the formula will enable us to take that into account. So the formula here is Q equals E sigma TH to the power of 4 minus TC to the power of 4 times A. Okay, so this looks a little bit more fancy than some of the previous ones. It's got a power of 4 in it for a start, which is kind of entertaining. So what we've got here is a whole bunch of things. So Q is exactly as we had before. It's the rate of heat transfer. So this formula is going to enable us to figure out how fast something is losing heat. E, it's not really an E, is it? It's an epsilon. Is what we call emissivity, of the object. And that's just a number between 0 and 1. Number between 0 and 1. Okay? So this is just measuring how well a particular object loses heat. And some objects lose heat better than others. Colour is one of the factors. How shiny they are, those sort of things will determine how well an object loses heat. So something which has got an emissivity of nothing doesn't lose heat, and something which has got an emissivity of 1 is a perfect radiator. Okay, sigma is what is known as the Stefan-Boltzmann Constant, named after a couple of physicists, surprisingly named Stefan and Boltzmann, and it's just a number. It's about 5.67 times 10 to the power of 8, negative 8. Get it right, it's a small number, isn't it? And the units for that is going to be watts, because you want to end up in watts. It's going to have to be per Kelvin to the power of 4, and we better have some square meters floating around in there as well to deal with the area. Okay, so 5.67 times 10 to the minus 8, it's a constant which you just have to use whenever you're using this formula. So it's basically a measure of how much power comes off something at a particular temperature and of a particular area of that material. And A, again, is the surface area. Okay, so if you wanted to figure out how much heat energy the sun was giving out, you'd need to know what the surface area of the sun was, you'd need to know what its emissivity was, and you'd need to know the temperature of the sun. And if you're just thinking about it radiating into space, and if we assume that space is pretty close to 0 degrees Kelvin, then you'd make this one 0. Space is actually about 3K. So that would be the area, the temperature of the thing it's radiating into. So TH and TC are the temperatures of the thing radiating and the space around it. So TH is temperature of the radiating body, must be in Kelvin, cannot be in Celsius, okay? Because now we're going to do this power of 4 thing. So when you do a power of 4, you're not just looking at the difference between two temperatures, you're doing the power of 4 and then the difference. So if you don't take it back to Kelvin, it'll stuff up. It must be in Kelvin. And TC is the temperature of the surrounds. Okay, so whatever it is that the thing is radiating into, that temperature is TC. And again, that must be in Kelvin. Okay, so we have this idea of being able to figure out how much heat energy is being given out by a body as long as we know these things. And we can do calculations going the other way. If we want to limit the amount of radiation to a particular amount, then we know the temperature inside and outside. So we could be thinking again about trying to insulate a home or a building and figuring out the temperature of the house is going to be 25 degrees, the outside temperature is going to be 10 degrees. How much is going to radiate? Well, the area is going to be one of the things that affect that. So we could figure out how much area we could have available to have only the desired heat transfer. Or we could figure out how much we need to change the emissivity by. So if we painted our object a different colour, how much would that affect the radiation? If we gave it a shiny surface, how would that affect it? All those sort of things that we can affect things with. But the key here is that radiation happens for everybody at any temperature, and it does not require a medium to take the heat away. So remember, conduction, particles don't move, but pass the energy from one to the other. Convection, the particles move and take the energy away with them. Radiation goes out and it doesn't require a medium through which it can move. And we have a formula for calculating how much is going on. So conduction, convection, radiation, the 3 ways of moving heat.